So, in this session we are going to discuss about the analogy between momentum and heat transfer. You see, from the governing rate equation, so this is the topic is momentum and heat transfer analogy. So, you see that momentum transfer tau yx, this momentum flux which is the shear stress, that is equal to mu into du dy, and we can write it, we have already discussed it, that it can be written as d dy of rho into u, right. So, this is basically the diffusion coefficient of momentum multiplied by the gradient of momentum concentration. This dt dy, right. So, this is minus of k divided by rho Cp into d dy of rho Cp T minus T difference. So, that is equal to alpha into H. So, that is the diffusion coefficient of heat or thermal diffusion coefficient multiplied by gradient of enthalpy concentration, right. Because here what is H is basically the unit will be joule per meter cube, right. Here for rho u the unit will be kg into meter per second divided by meter cube, right. So, you see that the units of nu and alpha, they are same unit of nu and alpha, and both are equal to meter square per second. So, this is a kind of similitude would exist between the rate laws. Now, we will go for more fundamental analogy which is called the Reynolds analogy. Now, see, for turbulent flow in a pipe, here for turbulent flow in a pipe, you see that tau is equal to, we can write it as nu plus epsilon m, that is the eddy diffusivity of momentum, into ddr radial coordinate of rho into u. Like I have a pipe, right, this is the radial coordinate, this is the radius. Let us say the pipe wall is maintained at Tw, right, and here we have an average velocity v bar, okay, and the local velocity u is a function of r. So, that is and epsilon m is the eddy diffusivity of momentum. Right. So, if I apply it at the pipe wall, so tau w is nu plus epsilon m into ddr of rho into u at small r equal to capital R. Now, from the definition of Fanning's friction factor, you know that tau w divided by half of rho V bar square is equal to F or FF, the Fanning's friction factor. We know that, right? So, tau W can be replaced by half of FF into rho V bar square, which is nu plus epsilon m into DDR of U at R is equal to capital R, and let's consider this rho as constant or invariant with this radial coordinate, right. So, this rho cancels out, and more fundamentally we get that half FF into V bar is equal to nu plus, or rather that divided by nu plus epsilon m will be the dimensionless velocity gradient at wall, right. This is the expression for dimensionless velocity gradient at wall. Now, similar to this, if I alternatively apply this Fourier's law as this alpha plus epsilon h, thermal diffusivity of energy, into dTdr, right, T rho Cp. Okay. So, DDR of T rho Cp, we are using it, and at wall, and Q alternatively is H into T wall minus bulk temperature of the fluid, which is a mean temperature, and it is equal to alpha plus epsilon H into DDR of T rho Cp. Right. So, this, and at wall we can write it at wall. So, dimensionless temperature gradient DDR of T divided by TW minus T mean, right, at wall is alpha plus epsilon H into rho Cp, or rather this is just the alternative, H into TW minus T mean, or TW minus T mean already we have included. So, H into H divided by rho Cp alpha plus epsilon H. Now, what was pointed out by Reynolds, that the temperature gradient, they will be same provided we have the same diffusivity expressions. How come this is true? You see that Navier-Stokes equation, not for pipe in general, for flat plate basically, this is applicable for any system geometry. For flat plate, we have U into del U del x plus V into del U del y equal to nu into del square U del y square. And energy equation, U into del T del x plus V into del T del y is equal to alpha into del square T del y square. So, if I convert this U and V into dimensionless form and T also in the dimensionless form, so if nu and alpha are same, we may expect same profiles of velocity and temperature in dimensionless form. And that is the basic idea here as proposed by Reynolds. So, what he did? He simply equated these two dimensionless One is velocity profile, another is temperature profile for pipe flow at wall, right? And considering equality of diffusivities, that is alpha plus epsilon h has been considered to be same as nu plus epsilon m, right, which alternatively implies that Prandtl's number is equal to 1. Okay. So, what he got? H divided by rho Cp is equal to H divided by rho Cp is equal to half Ff into V bar. So, H divided by rho Cp V bar, which is Stanton number, it's equal to Fanning's friction factor divided by 2, and that was Reynolds analogy. Right. Now, Reynolds analogy is restricted or valid for Prandtl number equal to 1. Right. Now, what is the meaning and why we are studying this analogy? The point is, see, Stanton number is proportional to heat transfer coefficient, and here we have Fanning's friction factor by 2, right. Now, in a system where we do not know the heat transfer coefficient, we can have a tentative guess about the heat transfer coefficient value, provided I have some idea about the friction factor. So, from one we are getting the measurement or tentative expression, or rather the measurement of the other. And here it is very, very important to note a contradictory feature, that if a pipe is rough, it has got a higher value of heat transfer coefficient, because if roughness increases, we know that friction factor also increases, right. So, if friction factor increases, definitely it predicts, this analogy predicts the heat transfer coefficient basically through Stanton number will also increase. Definitely that does not mean we will intentionally go for rough pipes, right, for higher heat transfer coefficient. That is not economically feasible. However, for rough pipe surfaces, right, with the same thickness of the wall, we expect higher heat transfer coefficient. Now, this Prandtl analogy was later generalized, the Reynolds analogy was later generalized by Prandtl, and here you see that it is a very crude rough analogy and alternatively valid for Prandtl number equal to 1. So, what I am trying to point out, you see that regarding Prandtl analogy, Prandtl provided a more realistic picture of turbulent transport by assuming the momentum and heat transfer occurring through eddy exchange or eddy transport in turbulent core and through diffusive transport in the laminar sublayer. So, what is important to note here, you see that in the Reynolds analogy, the 3 different layers what exist in fully developed turbulent flow in a pipe, that is a laminar sublayer, buffer layer and turbulent core, were not considered, right. And that has been mitigated through simply augmenting the diffusion coefficient by the respective eddy diffusion coefficient. But Prandtl correctly pointed out that heat transfer in the turbulent core, that mechanism will be different from that of laminar sublayer, and he separately considered 3 layers, right, with the assumption of using universal velocity profile that we have studied, which is u plus equal to y plus, then u plus equal to 2.5 ln of y plus plus 5 and so on, right. That is the universal velocity profile. Near the wall, Prandtl developed the following equation relating Stanton number and Fanning's friction factor. So, what is the correction? I am not going into the derivation is not required, you do not have to remember also this equation. Ff by 2 divided by 1 plus 5 under root Ff by 2 into Prandtl number minus 1. This is a more complex one, right, and that is Prandtl analogy. Right, so you can understand that Prandtl analogy is generalized, it is valid for any Prandtl number, and for Prandtl number equal to 1, it reduces to Reynolds analogy, right. Now, Chilton and Colburn, much later, this Prandtl analogy was developed in 1910. So, Chilton and Colburn in 1934, what they did? They simply replaced this one denominator, the entire denominator, by Prandtl number to the power 2/3. How they replaced, we will discuss it later, but we will not following this route. This was approximated as Prandtl number to the power 2/3, right? And they stated that Stanton number into Prandtl number to the power 2/3 as Chilton-Colburn factor JH. Chilton-Colburn factor for heat transfer, and that is equal to this friction factor by 2, right. So, that is Chilton-Colburn analogy, which is the most popular one, right. So, you see this Chilton-Colburn analogy, Prandtl analogy we do not use that much. Chilton-Colburn analogy is the most popular one. This Chilton-Colburn analogy we can alternatively derive from this any equation for the turbulent flow. You see that for C dot Tate equation, so what we have? We have Hd by K for pi flow, 0.027 into Reynolds number to the power 0.8 into Prandtl number to the power 1/3 into phi u. So, this Nusselt number, if I divide it by Reynolds number into Prandtl number, right, you get 0.027 into Reynolds number to the power minus 0.2 into Prandtl number to the power minus 2/3 into phi u. So, that is Stanton number. So, Stanton number into Prandtl number to the power 2/3 into phi u inverse, actually that in corrected form is the Chilton-Colburn factor, and that is equal to 0.027 into Reynolds number to the power minus 0.2. And from Blasius correlation of Flanning's friction factor, that can be established to be is equal to F by 2. So, this is typically the formal way of getting the Chilton-Colburn analogy is an easy manner, right. So, all this analogy and Chilton-Colburn analogy also reduces to Prandtl analogy, this Reynolds analogy for Prandtl number equal to 1. It gives you Stanton number, phi u is neglected, simply equal to Ff by 2, right. So, you see that we have just jotted down the three analogy, Reynolds analogy and Prandtl analogy, or this Chilton-Colburn analogy will be majorly used for, and actually more than its use, it has got its theoretical importance, right, more than in its use, because we have, if necessary, if I need an accurate measurement, I will go for dimensional correlations, right, conducting experiment, and therefrom we can get the expression of H as a function of, or in terms of Nusselt number mostly, as a function of Reynolds number, Prandtl number and pertinent other dimensionless groups of the system. But we can have, prior to that experiment, if I do not have anything, if I am starting from scratch, prior to that experiment, we can actually predict some range of this H, right, if I know the Flanning's friction factor of that system. So, that is the utility. Reynolds analogy definitely it's nowadays it's simply of historically important and valid for Prandtl number 1, that is valid for air. Okay. Air has got a Prandtl number equal to 0.7 close to 1. So, Chilton-Colburn analogy we majorly use, and that is why this Chilton-Colburn factor that has been tabulated with respect to Reynolds number in different design books. We will discuss that when we go for heat exchanger. Next. So, that is about the analogy of heat and mass transfer, or this heat and momentum transfer. Now, we have to understand the fundamentally important concept where we have to, so far what we have discussed, the different ways of calculating this heat transfer coefficient, right. Now, we have just mentioned that we have the very elementary heat transfer or heat exchanger device, that is the double pipe heat exchanger. So, in that system, if I know this inside heat transfer coefficient and outside heat transfer coefficient, that is HI and HO, by using this C dot A or this and conjugated with this idea of equivalent diameter, right. So, by some means or the other, now we are able to calculate the values of HI and HO. Now, once this HI and HO are known, next, how will you write it? How will you write the heat transfer? This overall heat transfer coefficient, the idea of overall heat transfer coefficient now we are going to discuss. Because HI and HO are the individual film or individual effective film heat transfer coefficient. What about the overall heat transfer coefficient? If I lump this into a single parameter, definitely that will be advantageous, right? And we can write that just following this same convection equation, that Q is equal to or over a specific section where the temperatures of these two fluid are constant, right. We can simply write that U into delta A into delta T, where delta T is the mean temperature difference. So, in order to understand the concept of overall heat transfer coefficient, fundamentally we have to understand the structure of double pipe heat exchanger. See, this is the double pipe heat exchanger, that is the inner pipe, say hot fluid or cold fluid, whatever, and in this direction we have the cold fluid. Right. Now, at any section, why we are considering the section? Because the temperature of the hot and cold fluid are progressively changing with the different location. So, at any section, if this is TH or if this is say TC, right, this is TH, the bulk temperature. So, here also it is the bulk temperature. Over this region, what is the temperature profile? And you have a metallic wall. So, you see, if I think that this is the metallic wall of the pipe, and on this side we have cold fluid, on this side we have hot fluid. So, what is the expected temperature profile under steady state? So, the thing is, it will be something like this. Right. This is TH, this is THI, TCI and TC. Why it is just like this? See, here we have flow of hot fluid, here we have flow of cold fluid, and let us say it is turbulent flow. Now, very close to the wall. So, again the very similar structure. If I think turbulent flow, this is laminar sublayer, this is buffer layer, and this is turbulent core or turbulent region rather. We should not say it's core, because for hot fluid, okay, it's fine, it's pipe flow, but for cold fluid there is actually the core, means it's more associated to circular cross sectional area. So, let us not go into that confusion that it is turbulent core or something else. So, let us say it is turbulent region. Now, see, in the laminar sublayer, the mechanism of heat transfer is conduction, and let us say the conductive resistance is R1. In the buffer layer, it is conduction plus convection, and in the turbulent core or turbulent region, it is purely convection, right. Let us say the thermal resistance is R3, here the thermal resistance is R2. So, it is pretty obvious that close to the wall the resistance will be maximum, right, because we have only conductive transport. So, R1 is greater than R2 greater than R3. Now, the rate of heat transfer or heat flux Q is proportional to respective temperature difference divided, or delta Ti divided by Ri. So, here let us say this gap or this difference is delta T1, this is delta T2, and this one is delta T3. So, respective temperature drop in individual layers. So, what we know that as under steady state, Q1 must be is equal to Q2 must be equal to Q3, the heat flow rate in the individual layers must be same. So, delta T1 divided by R1 is equal to delta T2 by R2 is equal to delta T3 by R3. As R1 is greater than R2, which is greater than R3, delta T1, the drop of temperature close to the wall, will be maximum compared to the second in the buffer and compared to that of third, which means the gradient, if I write it in terms of gradient, in close to wall will be the highest, and as we are moving away from the wall, it will drop down to 0 like here, right? And that is why this temperature profile, it is not like this. Now, under this actually it is not exactly correct, because it is finally a circular one, and for circular pipe we know that the profile, the velocity profile is parabolic, right? The profile is logarithmic, but here we have drawn a straight profile. Basically the idea is, as we are considering a very small thickness, so we can tentatively assume the steady state profile of temperature same as that what exists in a slab, right? So, it is typically linear we have considered, but truly it should be logarithmic, and the same will be followed, the same this logic will be followed in order to draw the temperature profile on the cold side fluid, that here it will have the maximum gradient and the gradient progressively decrease as we are moving towards the bulk. So, that is the basic idea of this temperature profile. So, with that temperature profile, you see we can think of an overall coefficient, right? An overall coefficient, just like if I consider this area of heat transfer, like we are considering this, if this is the central pipe, this area, right, here this. So, this area is dA, here the temperature is Tc, here the temperature is Th. So, you can immediately write that okay, dq is equal to some overall heat transfer coefficient into dA into Th minus Tc, right. So, immediately the question will arise that there actually are two areas. One is the inner area, because the pipe wall has got a thickness. One is the inner area, another is the outer area. So, we must base, or we must define the area, and respectively the definition of overall heat transfer coefficient will also change, right. So, we will write that dq is equal to UO dAO into Th minus Tc. So, this is based on outer area, and it can also be written as Uy dAi into Th minus Tc. So, evidently these two heat transfer rates are same. So, Uy dAi will be equal to Uo dAo. So, further Uy into pi into di into dl is this length, will be equal to Uo pi into do into dl. So, obviously here from we can write that Uy by Uo is equal to do by di. So, if I know one, we can immediately get the other using this simple ratio based relation, right. So, in the next section, in the next session basically we are going to discuss definitely that how definitely this ui or uo whatever it is, it's related. See, ui or uo, they are functions of hi and ho, right. So what is the nature of the functionality, and as the temperature changes, why we are getting, we should get this temperature difference, what I have written as Th minus Tc, this Th and Tc are progressively changing. So the thing is, there must be some average temperature difference, and that is that everyone knows that it is the logarithmic mean temperature difference. So why we are getting, what is the mathematical analysis by which we get this Q is equal to UALMTD, that we are going to discuss in the next session in addition to this functional relation. Thank you.